In this video, we'll continue looking at the limit process. Hi, my name is Dr. Ron and welcome to my channel. In my previous video, we learned that the limit process is an approach process where we answered the question, what value does f of x approach as x approaches a particular value? If you need to review that video, click on this link before going on. Here, we're going to look more at the limit process itself. What are its properties, and how do we solve limit problems? Let's get started. I've listed the limit results from last time. The limit as x approaches a, any real number, of the function x is simply a. It's a plug-in. The limit as x approaches any real number a of a constant c is equal to that constant. And the limit as x approaches 0 of 1 over x does not exist. Let's use these limit results and look at some of the properties of limits. The first of the limit laws says that the limit of a sum of two functions, f of x and g of x, equals the sum of the individual limits. In other words, I could take the limit of f of x first and individually take the limit of g of x and add them to get the limit of the sum of the two functions. This law also applies to a difference of functions, so I'm going to go ahead and write a minus sign underneath to indicate sum or difference of functions. The second limit property says that the limit of a product of two functions, f of x and g of x, equals the product of the individual limits. Taking the limit of f of x first alone, the limit of g of x, and multiplying that result gives me the limit of the product of two functions. The limit of a function squared applying rule B, or property B, says that the limit as x approaches a of f of x times itself, I could take the limit of f of x individually each time and finally rewrite that as the limit of the individual function and square that result. This idea can be generalized to any power n, where I would just simply multiply f of x times itself n times. And n could also be a fraction. For example, the square root of a limit equals the limit of the square root. Property D says that if I have a constant, in other words, a number, multiplied by a function, again, applying the second property of limits, I arrive at the limit as x approaches a of a constant c times the limit as x approaches a of the function f of x, and using this second limit result, where the limit as x approaches a of a constant is the constant, I could simply substitute that number or constant here and multiply it by the limit of the function by itself. Finally, the limit as x approaches a of a ratio of two functions, f of x and g of x, can be written as the limit of the numerator function divided by the limit of the denominator function. Of course, the limit of the denominator function cannot equal 0. Here's a little exercise that's worth doing that will demonstrate these limit properties for us. This is not a formal proof. That'll have to wait for a future video. Let's take the first of the limit properties, which says that the limit of the sum of two functions equals the sum of the limits. I've chosen two very simple functions to start out, f of x equals x and g of x equals x. We can take the limit as x approaches 5, a positive integer, easy to work with, of the sum of f of x plus g of x. Substituting the expressions for f of x and g of x, that is of x, gives us the limit as x approaches 5 of x plus x. Now we're going to take the limit. Once we do that, we're going to plug in the value of 5 for x here, following our first limit result from the previous video. We see that we get 5 plus 5, which equals 10. We can take the same approach for the right-hand side of this limit property. In other words, the limit as x approaches 5, in this case, of f of x, and the limit as x approaches 5 of g of x, again, substituting the expression for each function, taking the limit, which is 5 plus 5, and we see that we get the same result, 10. I highly recommend you take these same simple functions and go through on your own and demonstrate to yourself that the remaining limit properties hold. In other words, the left-hand side of the limit property equals the right-hand side of the same limit property. Here's a problem that more closely resembles one that you might get on a homework assignment or on an exam. I made up this problem so that we could use all or at least most of the limit properties that I've listed to the right. Given this particular function h of x, determine the limit as x approaches 1 of h of x, again using these limit properties. I first substituted the right-hand expression of this function for h of x. Again, I chose not to FOIL out this portion of the problem, x plus 2 times x squared minus 3, so that I could illustrate the product property of limits. The next thing I did was to apply the sum and difference property of limits across the entire expression. So I have a limit of the 4x cubed term, a limit of this product, and a limit of this quotient. Next, I applied the limit property that says that if I have a constant times the function inside of a limit, I could multiply the constant in front and take the limit of the remaining function. Here, I took the 4 outside and multiplied it times the limit of x cubed for this first limit term. For the second limit, which is a product, I use the product property for limits, and this gives me the limit as x approaches 1 of x plus 2 times the limit as x squared minus 3. In other words, splitting that as a product. Finally, I use the product quotient property, which says that I could take the limit of a quotient function and split the limit into the numerator and the denominator, and that's what I've shown here. In order to do the next step, I had to erase the limit properties written to the right so that I would have enough space. What I did in the next step is to apply the limit property that says that the limit of, in this case, x cubed can be written as just the limit of x, the whole thing cubed. I use the limit sum and difference properties here to write the limit as x approaches 1 of x plus 2 as the limit of x plus the limit of 2. Similarly, I did the same thing here with x squared minus 3, and I also applied the power limit property that I applied here for this cubic limit to this squared limit. Here's another constant, and then finally I applied the sum and difference limit properties to this quotient. Something that's important to notice at this point is that now all of the limits are either a limit as x approaches some value, in other words, this first limit result, or they're a limit of a constant. Here I have a 2, a 3, a 5, and a 7. That's the second limit result. We can use these limit results to rewrite this expression by simply substituting in some numbers. So let's do that next. What I've done is I've substituted a 1 for the limit of x as x approaches 1, which is this first result. And again, for the limit of a constant as x approaches any real number is just simply the constant. That's the second result. Here I showed it for the number 2, but the same applies for 3, 5, and 7. If we do this arithmetic, what we arrive at is that this whole thing equals -1. Therefore, we could write that the limit as x approaches 1 of the function h of x as defined here is equal to -1. If we look carefully at this green arithmetic line and we compare that with our simple algebra 1 substitution of adding 1 into x, we notice that they're actually the same thing. And this brings us to our first step when we want to solve a limit problem. Step 1 is to plug in the number a. I'm going to write this here. And this is the a from the limit. In this case, a equals 1 for this problem. When you plug in the value a into the function generating f of a, you're going to get one of three results. The first result is a real number, 1, -2/5, in that case a fraction. It could be a decimal, like -4.752, or it could be an irrational number, such as square root of 2, pi, or e cubed. It could even be a 0. If you get a real number, stop. That's the limit. That is the answer to the problem. The other two possibilities are you'll get a non-zero value, such as 5, divided by 0. Or, more interestingly, you'll get a 0 over 0, what's known as an indeterminate form. So what do we do with this 0 over 0 or undefined result? Click on this link for the next video to deal with 0 over 0. Or click on these links to review my past videos about calculus and the introduction to limits. I'll see you in the next video.